Hi there. Today we're going to talk about matrices, and what we're going to talk about is decomposing matrices into lower and upper matrices. The way we do that is using Gaussian elimination. Okay, so if you're not used to some of these terms, a lower matrix looks like the following. So it'll have values, these could be different. I'm just putting x as any number. So the values basically in the lower part of the matrix. So if you look at the diagonal, below that there'll be values, and that'll be a lower matrix. So everything above that will be 0. Okay, so that means there'll be zeros everywhere, which basically means that's a lower base matrix. Obviously, an upper base matrix, an upper matrix is the converse of that, so you'll have values in the upper region, which is interesting. And basically what we can do is we can use Gaussian elimination. So if you haven't done Gaussian elimination before, I'll give you an example here, but there are many resources to be able to work out how to do that. And we'll use Gaussian elimination to basically get the lower and upper matrices. Okay. So I've got an example here, as you can see. And this example comes from a website called lem.me. And I highly recommend going there because it's a fantastic linear algebra website which can show you basically how to do linear algebra from scratch. Okay, so what we're going to do is we're going to create our lower base matrix, and the lower base matrices are going to be a record of the steps we use in Gaussian elimination. So if we go here, first we're going to use elementary matrices, and those are based on the identity matrix. So if you're not sure what an identity matrix is, an identity matrix is the same as multiplying a number by 1. Okay, so if you get normal numbers, you've got the number 8, you multiply it by 1, you will have the same number. Okay, so in the form that I've written this just now, we have got, we're going to multiply something. Okay, so we're going to use A is equal to, A is the matrix, the lower bound matrix, which is this, multiplied by the upper bound matrix, which we're going to populate in a second. And we're going to multiply, if we multiplied the upper base matrix by the identity matrix, we would have the same value. Okay, so what we're going to use this matrix as a basis to manipulate the matrix that we've got for matrix A and to basically do Gaussian elimination. Very exciting. So if we look at the matrix itself, we can see that the first row there's a 3 in it, and the second row has got a 3 in it. So we can basically take the negative of the first row and add it to the second row, and basically that will eliminate the 3 in the second row. Okay, so that's what we're going to do. One other thing to note is we're basically taking a row perspective on this, because if you put a matrix on the left, the identity matrix on the left, and you basically want to use that as a product for the matrix on the right. So we want to basically use the row perspective on matrices. Okay, so let's go ahead and do it. So we're going to add -1 of the first row to the second row. So with this technique, we actually do the opposite of the multiplication sign. So if we're doing adding a negative, or multiplying by a negative, we effectively record that it's a positive. So that 1 means that it's actually a positive 1 on the matrix, but it's a negative 1 that we're multiplying by. So let's populate the first U that we have, just to make sure that we're all in the screenshot. There we go. So the first row will be the same as what it currently is just now. And then we'll basically add -1 of the first row to the second row. So it's -3 add 3 is 0. -5 add 8 is 3, -3 add 8 is 5, -2 add 4 is 2. The third row, as you'll see, we don't really have to do anything with because it's already got a 0 in the first column. So we're going to just proceed and copy that as is. And then the last piece of the jigsaw is we have to multiply the first row by 3 and add it to the final row to get rid of that first value in the first column there. So we said we'll multiply by minus 3. Sorry, we'll multiply by 3. So we record that as the negative of that, so that's minus 3 on our lower bound matrix. Okay, so let's go ahead. That's 0, minus 15, minus 3, minus 18, minus 9. Okay, so, sorry, 3 3s are 9, that's okay. 3 5s are 15. Got a bit wrong there. 3 5s are 15, minus 3 is 12. 3 3s are 9, plus 11 is 20. 3 2s are 6, and 6 is 12. So that's the first part of our Gaussian elimination complete. So what we'll do then, the lower bound of the matrix, is we'll basically take another kind of identity matrix, and at the end we're going to take the product of all these actions to basically have one L matrix. But we'll start off as we did before, and we'll create the identity matrix. As you can see, now what we're going to do is we're going to add minus 4 of the second row onto the third row. So we said minus, so that's going to be positive. Okay, so we're going to take another copy of U. This is just taking a copy so that we can track back if we make any mistakes. So 3 5 3 2. So the second row is going to remain unchanged. The third row is going to be minus 4 of 3s, minus 4 3 2. Minus 4 3s is 12. Add on 12 is 0. So it's 0. Minus 4 5s is minus 20. It's going to be 1. Minus 8. Add 10 is 2. We do the same thing to the final row. We're going to add minus 4 of the second row to the fourth row. So once again we'll have a 0 in here. Minus 2, 4 5s, minus 20, add on 20 is 0, that was convenient. Minus 4 2s are minus 8, add on 12, it's going to give you 4. So believe it or not, we've now gone upper matrix. As you can see, we've got the diagonal and we've got numbers above that, so that's given us the upper matrix. And we've got the lower matrix as a product of two matrices. So the next step that we're going to do is going to combine these two, basically just using basically the product of the two matrices. So let's go ahead and do that. As you can see, if we look at the rows perspective, 1 times that plus 0 times that row plus 0 times that row plus 0 times that row gives you the first row, so that's basically the first row. The second one is going to be 1 times the first row plus 1 times the second row, so that's going to give us 1 1 0 0. This is going to be 0 times the first row, 0 times the second row, 1 times the third row, so this is basically going to give us the third row. And then finally we've got minus 3 times the first row plus 1 times the last row. That's going to give us minus 3. There's no other values in there. I'm going to take the values as they are in the bottom row, and that gives us our combined L. How exciting. Now what we can do is to check that we've got the correct value for the lower bound matrix and the correct value for the upper bound matrix by multiplying or taking the product of the two matrices. Okay, so let's go ahead and do that then. So the lower bound matrix is 1 0. We're just going to take a copy of it just in case we go wrong anywhere, which has happened in the past many times. Minus 3 4 0 1. I'm going to multiply that by the upper bound matrix, which is 3 5 3 2. 3 5 3 2. 0 3 5 2. 0 0 1 2. 0 0 0 4. Okay, so L U is equal to that. So let's see what it's equal to. So that's the first row as it is, 3 5 3 2. We take 1 times the first row plus 1 times the second row. We're just going to add these together, so it's going to give us 3 8 8, 4. Awesome. We're then going to take 4 times the second row plus the first row, plus the third row, sorry. 4 times the second row plus the third row. So it's going to give us 12. Oh, hang on. 4 times 4 times the second row. 4 times the second row plus the third row. So it's 4 times 12. It's going to give us 12. 0, 12. 4 times 0, 4 times 12 plus 1 of them. 4 5s are 20 plus 1 is going to give us 21. That's going to give us 4 2s are 8 plus 2 is 10. Okay, looking good so far. And then finally we're going to have minus 3 of the first row times 4 of the second row plus 0 of the next row plus 1 of the last one. So minus 3, it's going to give us minus 9. It's going to give us minus 15. It's going to give us minus 15 plus 12, which is going to give us minus 3. Very good. This is going to give us minus 9 plus 20. Give us 11. And then finally, we're going to have minus 3 of those, of the 2. So minus 6 plus 8 is going to give us, okay, 3 2s, 3 2s. 3 2s is minus 6. Plus 8 is going to give us 2. Plus 4 is going to give us 6. Okay, so we've taken the product of LU. And as you can see, the reason I was looking up over here quite a lot is because when we take the product of L and U, that gives the example, the answer is A. So what we've done is we've decomposed the A matrix into L and U. And that works for both square matrices as we've just done, and it also works for non-square matrices as well, which is fantastic. There's one exception to the rule where you don't always have a lower matrix here, where you have to basically switch columns or switch rows. So if you have to switch rows, then you will lose the lower. It won't look like a lower matrix anymore. But it's generally accepted, I believe, by the mathematicians that conceptually it's a lower base matrix. We've just switched rows, so it still works. So the one exception where it might not work still works. Okay, so thank you if you've enjoyed the movie. If you enjoyed the video, please do not hesitate to hit the subscribe button because there's more coming your way. Thanks.